Hey everybody, Dr. A here, and in this video we're going to be exploring an example dealing with distributed loading. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. Alright, let's get started.
In this example, we're being asked to compute the resultant force and its location from point A. And point A is going to be this leftmost support or leftmost point shown here. So let's take a look at this loaded member that we have. It's 5 meters long, and we have this uniform load piece right here. And then on top of that uniform load segment, we have this triangular load piece, or this linearly varying load. So one thing to note is neither of these are given in function form. We could write a function for each of these, or one altogether, and take the integral form of this, or we can use geometric properties since these are pretty simple shapes. So that's the approach that we're going to take in this example, is using geometric properties. The first thing I do want to point out is the height of the rectangular portion, the uniform load, is 1 kilonewton per meter. That's the intensity of it. And then the intensity, or the height of the triangular portion alone, is actually 2 kilonewtons per meter. Notice that this dimension line is the 3 kilonewtons per meter is including the rectangular portion. So we need to make sure we recognize that the triangular portion alone is 2 kilonewtons per meter, while the rectangular portion is 1 kilonewton per meter. So under the solution, the first thing I'm going to do is I'm going to say, let's use geometric properties instead of the integral form. And again, the reason why is when you have simple geometric shapes like rectangles and triangles, or in this case, the rectangle and the triangle collectively make a trapezoid, it's better just to use geometric properties. There's really no need to develop a function and write an equation and take the integral. The integral form is best whenever you have a distributed load that takes the shape of some kind of function, all right, which is not what we have here. So the first thing I'm gonna look at is the rectangular portion. Okay, so I'm gonna call the equivalent force for the rectangle equal to the area of this rectangle right here. Okay, we've seen that before. So that's going to be 1 kilonewton per meter times 5 meters. And of course, that's 5 kilonewtons. Now, we should remember where this is located. For a uniform distributed load, the equivalent point load is located in the middle of the load distribution. So I'm going to sketch this out for us in just a minute. The next thing we need to recognize is the equivalent load for the triangular portion, okay, which is going to be this triangular piece right here. And again, it's the area of that triangle, so we have 1/2 base times height. So we're going to say 1/2 times 2 kilonewtons per meter times 5 meters. And so in this case, we are also clearly going to get a value of 5 kilonewtons. It just happens to be the same number as the rectangular portion, but that's just because of the values that we have here in this illustration. So you don't just memorize this and think that they're always going to be equal. It's completely based on the numerical values we have here in this specific problem. And we should remember from our previous videos where the equivalent load for a triangular distribution is, and that's 2/3 of the length from the tip here, or you could look at it as 1/3 of the length from the back face. So right now what I'm going to do is draw an equivalent system based on these two equivalent loads as they are now. So right here we have F rectangle, which is 5 kilonewtons. And then over here, we have F triangular, which also happens to be 5 kilonewtons. Now, where are these dimension lines? Well, if we draw all of these out, we're going to have dimension lines kind of like this, okay? So we've got 2.5 feet and 2.5 feet. and you can definitely see that that's the dimension line for the rectangular load, equivalent rectangular load. And then what about the equivalent load due to the triangular load? Well, that's going to be 2/3 of 5 feet. So we can say 10 over 3. So that would be 3.33 feet. And from the other point, that would be 1.67 feet over here. Okay. Now we're not quite done yet, right? This is point A. So the total equivalent load, or total resultant load, is going to be, I'm going to call it like F sub R, and that's going to be the sum of these two, F rectangle plus F triangular, and that's going to be a total of 10 kilonewtons. And so again, another way we could have gotten that is we could say, well, the total load is this entire area underneath this entire load diagram. You could have used the area of a trapezoid to get to that conclusion of 10 kilonewtons, and that would be fine. So this is part of our answer. Now, the next question is, how do you get its location measured from point A? Well, again, it's still a centroid location, right? It's still definitely a centroid location. So how do we calculate that? Well, we're going to use the summation form of the centroid formula. So remember from calculus, when you have discrete shapes or discrete values, we typically use the summation form instead of an integral form to add things up. But we use integral form when we have a function representation. So the summation form is going to be x bar equals, and we're going to have the summation of x sub I times x sub I times, look at that, times f sub I as I goes from 1 to n, divided by the summation of f sub I as I goes from 1 to n, where n equals the number of forces. Okay, so this is just the summation version of the same integral formula we've seen before, and we're able to use this summation because, again, we don't really have functions here. We just have simple shapes, and we've already resolved them into their own individual forces. So substituting values in, I'm going to say x bar equals, and I'm going to say f rectangle, which is right here, times its perpendicular distance to point A first, okay? So we're going to say f rectangle times 2.5 meters plus f triangle. And what do you think we're going to multiply f triangular by? So we got f triangular times its perpendicular distance to point A, which is the 3.33 meters, and then we're going to divide that by the total resultant force. Well, check out what this denominator is. When we say sum of all the forces in the system, well, of course, that's going to be the resultant force. So we would say 5 kilonewtons plus 5 kilonewtons. So again, kind of punching this out, we're going to have 5 kilonewtons times 2.5 meters plus the other 5 kilonewtons times 3.33 meters divided by 10 kilonewtons. And when we punch this through, let's see what we get. 5 times 2.5 plus 5 times 3.33, and then divide all that by 10. And so I get 2.915 meters. And so that's going to be somewhere in this vicinity right here. So our final equivalent system is going to look something like this. Here is F resultant of 10 kilonewtons, and here is x bar equals 2.915 meters. And then this distance right here is 2.085 meters. And this value right here, x bar, is part of our answer. And if you want to draw this equivalent system, the final equivalent system, you can right here. Equivalent system. So again, you know, we've done the same kind of thing, but what's different here is since we had simple enough shapes like a rectangular portion and a triangular portion, we have multiple simple shapes. We just used the summation version of that that equivalent, the x bar equation, okay, instead of the integral version. So make sure you are familiar with this as well. There's no need to set up a complicated integral equation necessarily if you have simple enough shapes.